Welcome back, everyone. In this video, we are going to learn a couple of skills that will allow us to analyze problems and scenarios using Newton's second law. So the first thing we're going to learn is how to create something known as a free body diagram, and then we'll use that free body diagram to actually use the second law in a scenario. So let's go ahead and jump right in. To start, this thing known as a free body diagram, it's a type of picture, and it's a picture that's used to visualize the forces acting on an object. Okay? And it's nice because it's a standardized diagram, meaning we use the same kind of set of rules for everything regardless of the object. And that's helpful for people like me who can't draw, say, a rocket or a spaceship or a car or a cow. So this standardized way of diagramming objects is helpful, and it's a simplified way. You don't have to worry about looking at each individual object and the different shapes and sizes that they come in. So a free body diagram, or FBD, it represents forces on an object, but also the direction the forces are acting. That's the key idea too, because knowing what direction these forces are acting, that's going to help us apply Newton's second law, as we'll see in our example in just a moment. There are some rules. This is how you draw a free body diagram. The rules make it seem more difficult than it really is, but here's what they say. It says we first draw a dot like this. Easy, there's a dot. The dot symbolizes the object. Like I said, I can't draw a car or a sheep, so the dot is our representation of our object. So there's our object, and then we draw arrows starting from the dot. That's actually an important rule. We always start from the dot, and we point away in the direction a force is acting. So let's say somebody was pushing this object to the right. I would start on the dot, and I would draw an arrow pointing to the right. Please excuse my poor drawing abilities with my tablet. If there is a force acting upwards on the object, I would start on the dot and draw a force upwards. Ignore that arrow, just like that. All right? So that's the second rule. And then we just repeat that for all the different forces. If there are 6 forces on the object, I would draw 6 arrows. If there were only a single force on an object, I would just draw 1 force. Okay? So that's it. That's a free body diagram. It helps us visualize all the forces that are acting on something. So let's do this actually with a scenario. That's the best way to just get good at this, right? We're chopping onions. Here's a question. It says 2 friends are moving a box. Each is exerting a force to the right, and there's a frictional force acting to the left. It's just to draw a free body diagram of the box and also to set up an expression for Newton's second law. So let's do this first one. Let's draw a free body diagram for the box. What do I do first? I draw a dot. Perfect. That represents this, my box. Let's think of all the forces that are acting on the box. Well, the box is on Earth, so I know that there's weight. So there should be a force acting straight down. I like to use the letter W. If you watch my earlier videos, you know the symbol isn't important as long as it's clearly labeled. The box is being supported by the ground, right? The box isn't falling into the earth. It's staying more or less on this grass, it looks like. So there must be a support force, what we call a normal force, acting upwards. Bam. Okay? Now, I have multiple forces acting to the right. I have this person pulling to the right with, looks like a string. So I'm going to have a force going to the right, and maybe I'll call that T for tension. Because it looks like, there's a tension force. They're using a dangler acting to the right. Now, there's also this person pushing to the right. So there's a few ways you could diagram it. Some people like to just make another arrow close by. I know maybe we're not exactly touching the dot, but that's okay. Let's call that maybe a pushing force. I'll call that P. Another way you could do it, this is a little less common, but some people might draw like T, and then they might have another arrow going like this for P. I don't see that too often, but that's also a valid way to do it. I like this way, but either one. There's also, it says, a frictional force acting to the left. We're going to learn more about friction later. This one is actually telling us, this question is actually saying there's a frictional force to the left. I'm going to use a little F like this. Okay, so that's a frictional force between the box and the grass, and friction opposes sliding motion. So that's it. That's our free body diagram. These are the forces acting vertically. These are the forces acting horizontally. Tension, this pushing force, sorry, maybe I should have made that a bigger P. It's not a subscript of N. P like that. There's a frictional force and there's weight. These are all the forces. Now, what does it mean to set up Newton's second law in the x direction? Well, it means we're going to apply the second law. Remember, that means this. Net force equals ma. That's the second law. But let's apply this for this scenario. And this is why this unit can be challenging for students. When we were studying motion, all the equations were given to us, right? Think of those constant acceleration equations. But now in this unit, you are actually creating the equation. Because Newton's second law is actually pretty vague. It says when you look at the total number of forces acting in a particular direction, that equals ma. But it doesn't say what all the forces are. And of course, that could change based on the scenario. So you're actually creating an equation almost from scratch based on a particular problem. So what does that mean? In the x direction, this maybe isn't super important now, but I even like, because I'm trying to be as organized as I can, I sometimes even like to label this as horizontal. I'm going to set up Newton's second law, look at the sum of the forces in the x direction. What does that mean to look at the sum of the forces? I am literally going to list the forces, and I'm going to either add or subtract them, okay? Now, I never actually indicated my positive and negative direction. That's normally something I want to do. Let's say to the right is positive, and let's say upwards is positive. That's pretty typical. So, what forces are acting horizontal? Notice I put a colon. I'm going to list all the horizontal forces. Let's see. There's this tension force. That's acting horizontally. Should that tension be a positive force or a negative? It should be a positive because tension is acting to the right according to my free body diagram, and that's in the positive direction. Now there's also this pushing force. I'm going to write P. Should this P be added or subtracted? This pushing force should be added. Remember, these are vectors, okay? Direction is a crucial part of their information. Both these vectors are in the same direction. I'm adding forces. I am adding vectors. So it's important to keep their direction, and we indicate that by their sign, positive. So that should be positive. Last force, friction. I have this F. Should I be adding friction or should I be subtracting? I should be subtracting because the frictional force, it's a vector. It's acting in the opposite direction. Friction is opposing. You can probably imagine that two forces in opposite directions, they're fighting each other. Again, this is a vector. You can't just say plus, 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 plus. That would only be like, adding up the magnitudes or the absolute values. These are vectors. You have to keep direction into account, and we do that with pluses and minuses. So it's the tension force and the pushing force. Notice these are being added. That tells me, the reader, that these are being added. And there's another force, friction, that's acting in the opposite direction. This right here, this is the sum of the forces. And according to Newton's second law, the sum of the forces is equal to, mass times acceleration, right? There we go. I had to squeeze it in. My apologies. So this is the sum of the forces right here, and this is what Newton's second law says the sum of the forces are equal to. So this is it. This is me doing this second bullet point. There's no numbers for me to plug in. I can't go any further, but I drew a free body diagram, and based on the direction of those forces and the direction I said was positive or say negative, I knew to either add or subtract these vectors together. By adding and subtracting, that's my sum of the forces, and it's equal, according to Newton's second law, to the mass of the object, the box in this case, times acceleration. So this is what we're going to practice. And of course, we'll see some practice where there's numbers involved, but it's crucial that you get good at drawing free body diagrams because that's almost always required, or at least it's good practice because it tells you exactly what to write when you then try and apply the second law. It doesn't ask me to do this for the vertical direction, so I'm going to stop right here, but we could do something similar, and we'll get practice doing something similar in the up and down, the vertical direction. But I'm going to stop here. Thanks a lot for watching.